Good day, everyone. Welcome to my Philosophy 1 presentation. I am Johan Zach G. Tolentino, a first year student from Babi 1B 2022 in UB Clark. Today, I will discuss certain chapters from Reading 5, The Structure of Scientific Revolutions by Thomas S. Kuhn. We'll be tackling the following chapters. First in the list will be Chapter 4, Normal Science as Puzzle Solving. Next is Chapter 5, The Priority of Paradigms. Chapter 6, Anomaly and the Emergence of Scientific Discoveries. And finally, Chapter 10, Revolutions as Changes of Worldview. First, let's get to know our author and the book. The author is Thomas S. Kuhn. He is one of the most influential science philosophers back in the 20th century. He's the one who wrote the book that reached a lot of scholars worldwide, as the book is one of the most cited academic books of all time. By also this book, he was able to contribute the following: positivist doctrines in the philosophy of science and the creation of a new style that brings philosophy of science and history of science closer together. As for the book, it is called The Structure of Scientific Revolutions. It was made in the 19th century and it is a classic work in the field of philosophy of science. It mainly argues that science develops throughout time by adding more truths to the stockpile of old truths, by challenging previous scientific worldviews. Starting off with the first major bit of the presentation, Chapter 4, Normal Science as Puzzle Solving. In this chapter, Kuhn defined normal science. Normal science is defined as a type of science in which scientists have no intention aiming for new knowledge, but to affirm what has already been discovered. It works by scientists familiarizing themselves with what has already been discovered along with sets of beliefs and practices from their academic training. When it comes to scientific work, they match the expectation of their beliefs to the result as much as possible. With that taken into account, why is it related to puzzle solving? In puzzle solving, with an unfinished puzzle on hand, we already know what the result will be without even fully solving it. The same applies to normal science. In normal science, we already know what the result of a certain scientific work will be without solving it just yet. Now, Kuhn proposed a scientific question regarding this. Even though the scientists know what the result of the scientific work will be, and proceeding on it will result in nothing new, why still pursue it? He said it is still worth doing because it tests and sharpens the skill and ingenuity of the scientists and reminds scientists the best way in approaching the end of the scientific work. To add more details about the matter of normal science as puzzle solving, let's view it from the eyes of Thomas Kuhn himself and give it four analysis. First, normal science as a puzzle is a perplexity. One is confined by a phenomenon that one does not understand, either in the context presented or in terms of the conceptual framework one already has within which one makes sense of the world. To make this clear, this does not mean that normal science is aiming for something wholly new by touching on something that one does not understand yet, which is a contradiction to its original definition. It is rather touching on something new to you, which everybody else knows already. In other words, you're going to do normal science towards an already discovered work that is new to you but not for others. I hope that's clear. Second, a puzzle requires a logical way to its solution. Like a real puzzle, it has an instruction or set of rules to utilize and guide the player to the end. To give it a better description, imagine a puzzle that you're working on alongside an instruction. It's easy to imagine, right? Same goes for normal science. Imagine you're a scientist and a supreme scientist gave you academic training and ordered you to solve a problem regarding basic atomic science, let's say. The atomic science problem is the puzzle in this case, and the academic training the supreme scientist gave you is the instruction. That's how it's perceived. That's how you see the parallelism, right? There's a logical way to the solution of the scientific problem. Okay. Third, with regards to the first and second previous ideas, the solution of the puzzle has to fit within a prepared set of acceptable types depending on the rules given the process of solving it. For example, you're researching something and you created a hypothesis. At the time you set a hypothesis, you already applied a prepared set of acceptable standards that depend on your own rules. This, in other words, is called a paradigm as well. This is because you have established a worldview towards the research problem you're researching about. Once you've met the end of the research, is either you approve your hypothesis or not. If it is approved, that is nice. That is called a normal science because you just affirm your own paradigm. If not, then that is not normal science because your hypothesis or paradigm was challenged and possibly changed depending on your choice to keep it or adapt to the discovery. As you can see, it also parallels itself to normal science. No? A paradigm is set and the end meets the expectations of the paradigm. If not, then that is not normal science. Alright? So with that out of the way, let's move on to the next chapter. Chapter 5, The Priority of Paradigms. In this chapter, Kuhn's main objective to sketch the general character of scientific inquiry. To that end, he distinguishes and identifies the connection between rules, paradigms, and normal science. We'll be tackling numerous assertions by Thomas Kuhn. First in the list, he claimed that theories are illustrated by conceptual, observational, and instrumental application, and these became the community's paradigms, revealed in their educational system. Paradigms of mature science, according to him, are easy to discern, but the rules are not. By this assertion, Kuhn signals that paradigms are not identical or reducible to a set of rules that dictate scientific activity. Rather, a paradigm is a model for problems and activities. He also puts some emphasis on the rules that guide scientific activity. According to him, the rules are the source of continual and deep frustration because they are not easily comprehensible in abstract, but through application only. This is also why scientists are having difficulty articulating these rules. In line with that, he claimed that the prioritization of paradigms over the rules that govern ordinary science is justified by their centrality in the scientific community established around them and their critical position in the education of aspiring scientists. Lastly, Kuhn argues that it is a mistake to prioritize rules governing certain activities over paradigms. Rather, as models, paradigms integrate different research activities in ways rules cannot. Now, what does this all mean when combined? Well, in conclusion, Kuhn claims that science is a social activity. The training and experience of practitioners within a paradigm determine the rules governing their activity. All in all, it goes down to the quote, practice precedes rules. Right? Let me elaborate on that. In this chapter, Kuhn pointed out that science education majorly involves learning by practicing. So, what intimately connected here is the scientists and their activities. They never separate. They keep doing and doing and doing. This observation leads to an interesting feature of science, which is its pragmatic nature. If we're going to recall what pragmatism is perspective in which the person at play does not care if his means or methods are true, ethical, sound, etc. As long as it is a success in the end, an experiment shows a result, there is no problem. If we're going to connect practice in the concept of science, pragmatism is well applied because practice has a goal to reach. It does not matter whether the process of reaching that goal is true, sound, ethical, whatever you call it, as long as it reaches the goal of the practice, say reach the hypothesis, it's all good. Okay? That is science. That's why we have lab rats for testing. It may be unethical to utilize living beings to reach the scientist's goal in learning something new, but science has to keep learning, right? To generate more knowledge. That is pragmatism at play. Right? Now let's move on to the next chapter, shall we? In the next chapter, we'll be talking about anomaly and the emergence of scientific discoveries. In this chapter, Kuhn focused on anomaly. Anomaly, in general terms, is an expected occurrence. When put into the scientific context, it is an unexpected occurrence or result from a scientific work. In science, it is normal that it often appears in ways that are either not seen, ignored, or dismissed. Let's say in an experiment, you know what the results will be. However, when the result finally came, you receive a different outcome that is unexpected, right? That's what you call an anomaly. All right. Moving on to the next element of the chapter, the paradigm change. Paradigm change is the change of view towards a particular matter. According to Kuhn, paradigm changes are possible and can happen in two possible ways. First, through discovery, and second, through new facts and theories. Paradigm change happens through discovery when a novelty appears from a scientific work because it is a novelty. It is something new and it forces scientists to change paradigms to adapt to the novelty, right? As for paradigm change in terms of new facts or theories, this happens when new facts and theories are incorporated in a scientific work to result into something new. Because of this, the previous paradigm is affected and possibly replaced by a new paradigm, thus causing a paradigm shift. In line with this, Kuhn added that the anomaly can be identified as well when nature somehow violated the paradigm induced expectation that govern normal science. Kuhn gave three examples of novel anomalies in this chapter, and these are namely the discovery of oxygen, the Leyden jar, and the X-ray. To give an example, we'll be using the discovery of oxygen. So the question is, how was it a novel discovery? Before, oxygen was not believed to be part of creating combustion. What people know was that combustion was only the process by which a burning object releases the element phlogiston. However, after further examination and exploration of the topic, oxygen was eventually discovered in the process of combustion. Along the way, more and more anomalies appeared after each conducted experiments. Eventually, anomalies forced the paradigms toward oxygen to change and thus became a novelty. To add to this, let me give an example from personal experience. Right? Consider this as as an analysis coming from me, since I'm applying what I've learned from this example. For us unprofessional scientists ourselves, we can give our own example of a novel discovery. Like the oxygen scenario, when I was a kid, I had a set of beliefs that pertains to the size of the world is only the size of a house. I never thought of it expanding one day. When my curiosity hit as a child, I tried experimenting to test whether my set of beliefs will be challenged and changed or not. So I tried to escape the house. When I got outside of the house, I was shocked because my beliefs were indeed challenged and changed. The world was bigger. There is a town outside of my house, and the world gets bigger and bigger as I age. Now, that is a novel discovery because I learned something new and I didn't affirm what I already know, right? Unlike normal science. So that's my take. And let me also add another one that is interesting. As I analyze the correlation between the puzzle and anomaly under normal science, I have observed that the two are directly connected to each other, especially in the way that anomaly is a powerful game changer of the puzzle under the context of normal science. Let me explain once again. First, let's imagine it as a literal puzzle. Recalling the two concepts, basically, the puzzle is the game field of our scientific work here. We are here to solve a problem and expect an inevitable result. As for anomaly, it is an expected result that may come out at the end of the scientific work. Now, the relation of anomaly here is that once we discover it at the end of the problem, we find ourselves a new discovery, an unexpected outcome, right? Because of that, the game will change, the rules will change, and a new puzzle game will start once again, leading us back to square one, but on a different level. That's how powerful an anomaly is, and it is the key to enriching our knowledge of whatever it is in the world. So once again, that is my take. Okay, so lastly, the last chapter, chapter 10, Revolutions as Changes of Worldview. In this chapter, Kuhn began with pointing out the past revolution era of a scientific problem. In this era, scientists observe a different problem. A different world. Familiar objects to them are seen in new ways, and unknown objects become visible. He emphasized here that the world has not changed, but rather the perception of whoever is looking. In this scenario, this is what he calls a shift. It only occurs when the existing paradigm no longer fits, or when nature no longer fits in the paradigm. According to Kuhn, the change is something like the Gestalt shift. The Gestalt shift is a phenomenon when a person views a single image, but the second time he or she looks at it, it's a different image. A classic example of this will be the duck rabbit on the right side of the screen. Looking at the image, you may first see either a duck or a rabbit only, but the second time you look at it, it is different. It may be a duck or a rabbit this time, whatever whatever animal you started with. Now, Tukun, this is like science. Prior to the revolution, it was not possible to see two perceptions. Now, in the post-revolution, once you've discovered an anomaly and there's a new discovery, both can be seen simultaneously, right? Now, to expand on this chapter, because it's quite short, let me give an analysis. What I think Kuhn is trying to say here is that the understanding of a scientist is limited by the paradigm in which he or she works. It is a very disturbing idea to many scientists because scientists also believe in the limitless universe in which science plays upon. Yet the scientist is limiting himself or herself to the paradigm he or she has. Quite ironic, isn't it? Now, what I think is limiting himself or herself to the paradigm. Now what I think can be done here is that the scientist can also utilize his or her paradigm as an advantage as well, as a basis for finding something new out there. Let's take the gestal shift rabbit duck image as an example. At first, you see a duck. Now that you have an animal in mind, your mind can think of something else that is also an animal. So when you look at the image again for the second time, it can now be a rabbit. If you're going to be more creative, perhaps change the angle, like let's say you put it upside down or to the right or the left, you might get another image. It might be a carrot, an elephant, you name it. So that's my take here. All right. So in conclusion, we have discussed the four chapters with each of its own takeaways. First, normal science is like puzzle solving. Second, science is more of a social activity. Third, discoveries are caused by anomalies. And lastly, as the world changes, the world does not change, but one's own perception. All right. Here are my references and my credits to the original owners of the elements of this presentation and the pictures I've used. They're all not mine. And that is all for my presentation. Thank you very much for listening. And I hope you enjoyed.